To estimate the wattage of a 1.5 horsepower electric motor operating at 480 volts, we can begin by converting horsepower to watts. The conversion factor is 1 horsepower equals 746 watts. Therefore, 1.5 horsepower multiplied by 746 watts per horsepower equals 1119 watts. This calculation provides a baseline estimate. It's important to understand that this is a simplified calculation and the actual wattage drawn by the motor can vary. Factors affecting wattage are resistance and efficiency. The initial attempt to calculate wattage using Ohm's law and assuming a resistance of 1 ohm is unrealistic for an electric motor. Electric motors are not purely resistive loads. They are inductive loads, and this significantly affects the current draw and power consumption. Secondly, the current calculated using the simplified Ohm's law of current equals voltage divided by resistance is incorrect in this context. The impedance of the motor windings is far more complex than a simple resistance. The power calculation, using wattage equals voltage times current, is also incorrect due to the inaccurate current value. Electric motors are not 100% efficient. Some power is always lost due to heat, friction, and other factors. The efficiency of a motor is the ratio of the mechanical power output to the electrical power input. Efficiency is typically expressed as a percentage. A typical electric motor will have an efficiency rating which can vary, but it is usually in the range of 80% to 95%. This means that for every 100 watts of electrical power consumed, the motor will output 80 to 95 watts of mechanical power, with the rest being lost as heat. To determine the actual wattage, firstly, find the motor's full load amperage of law from the motor's nameplate. This value is crucial for accurate calculations. Secondly, use the following formula to calculate the approximate wattage. Wattage equals voltage times amperage times the power factor. The power factor is a measure of how effectively the motor uses electrical power. It's the ratio of real power, measured in watts, to apparent power, measured in volt-amps. The power factor for an electric motor is typically between 0.7 and 0.9. If the power factor is not known, a value of 0.8 is commonly used for estimation purposes. For a 480 volt motor, the formula becomes wattage equals 480 volts times the full load amperage from the motor nameplate times the power factor. For example, if the motor's full load amperage is 3 amps, and assuming a power factor of 0.8, the wattage would be 480 volts times 3 amps times 0.8, which equals 1152 watts. This value is more representative of the actual power consumption of the motor. The initial calculation of 1119 watts, derived directly from the horsepower conversion, provides a rough estimate of the motor's output power, that is the mechanical power it delivers. The second calculation of 1152 watts, incorporating the full load amperage and power factor, provides a better estimate of the motor's input power, that is the electrical power it consumes. It's important to consult the motor's nameplate for accurate values and consider the motor's efficiency and power factor for realistic power consumption estimates. Actual power consumption can vary depending on the load in the motor. If the motor is running at less than full load, it will draw less current and consume less power. If the motor is overloaded, it will draw more current and could potentially overheat or fail. When installing or maintaining electric motors, always refer to the manufacturer's specifications and follow all applicable electrical codes. For accurate calculations, always refer to the motor's nameplate data for voltage, full load amperage, service factor, and other relevant information. The National Electrical Code, or NEC, provides guidelines for electrical installations, including motor circuits. Article 430 covers motors, motor circuits, and controllers. NEC Table 430.248 and NEC Table 430.250 provide full load currents for motors. These tables are used to determine the appropriate conductor size, overcurrent protection, and disconnecting means for motor circuits. Always consult the latest edition of the NEC for the most up-to-date requirements. When selecting overcurrent protection for motor circuits, it's important to consider the motor's starting current, which can be significantly higher than its full load current. The NEC allows for higher overcurrent protection ratings for motors to accommodate this starting current. Refer to NEC section 430.52 for specific requirements on motor overcurrent protection. When sizing conductors for motor circuits, consider the motor's full load current, the ambient temperature, and the number of conductors in the raceway or cable. The NEC provides ampacity tables for conductors in NEC Table 310.16. The rating factors may be required based on the ambient temperature and the number of conductors. Use appropriately sized conductors to ensure safe and reliable operation of the motor. Grounding is essential for electrical safety. Motor frames and enclosures must be properly grounded to prevent electrical shock hazards. Refer to NEC Article 250 for grounding requirements. Use a grounding conductor sized according to NEC Table 250.122 to connect the motor frame to the electrical system ground. Regular maintenance is essential for ensuring the long life and efficient operation of electric motors. Maintenance tasks include lubricating bearings, cleaning motor windings, and inspecting connections. Follow the manufacturer's recommendations for maintenance intervals and procedures. If the motor is located in a hazardous location, such as an area with flammable gases or dust, special precautions are required. Use motors and electrical equipment that are approved for use in hazardous locations. Refer to NEC Article 500 through NEC Article 516 for requirements on electrical equipment in hazardous locations. For 480-volt motors, it's important to use properly rated components, including conductors, overcurrent protection, and disconnecting means. 480 volts is a higher voltage than 120 volts or 240 volts and requires greater insulation and clearances. Use components that are specifically designed and rated for 480-volt applications. When working with electrical equipment, always follow safe work practices, including wearing appropriate personal protective equipment, such as gloves and eye protection. De-energize circuits before working on them, and use lockout-tagout procedures to prevent accidental energization. If you are not qualified to work on electrical equipment, hire a licensed electrician. The information provided here is for general guidance only and is not a substitute for professional electrical engineering advice. Always consult with a qualified electrician or electrical engineer for specific applications. Improper electrical work can be dangerous and can result in property damage, injury, or death. When working with electrical systems, always follow the applicable electrical codes and standards. The NEC is the primary electrical code in the United States, but other codes and standards may also apply, depending on the location and application. Understanding the fundamentals of electrical theory is essential for working with electric motors and other electrical equipment. Electrical theory covers topics such as voltage, current, resistance, impedance, power, and energy. A good understanding of these concepts is necessary for troubleshooting and maintaining electrical systems. Electric motors are used in a wide variety of applications, including pumps, fans, compressors, and conveyors. The type of motor used depends on the application requirements. Different types of motors include induction motors, synchronous motors, and direct current motors. Each type of motor has its own advantages and disadvantages. When selecting a motor for a particular application, consider factors such as efficiency, torque, speed, and environmental conditions. The motor's service factor indicates the amount of overload that the motor can handle for a limited period of time. A service factor of 1.0 means that the motor can operate continuously at its rated horsepower. A service factor greater than 1.0 means that the motor can handle a temporary overload. Do not continuously operate a motor above its rated horsepower, as this can cause it to overheat and fail. Variable frequency drives, or VFDs, are used to control the speed of electric motors. VFD can save energy by reducing the motor's speed to match the load requirements. VFD also provides soft-starting capabilities, which reduce the stress on the motor and the driven equipment. VFD are commonly used in applications such as pumps, fans, and conveyors. When installing a VFD, it's important to follow the manufacturer's recommendations for wiring and grounding. VFD can generate harmonic currents, which can interfere with other electrical equipment. Harmonic filters may be required to mitigate these harmonic currents. Electric motors can be single-phase or three-phase. Three-phase motors are more efficient and provide smoother operation than single-phase motors. Three-phase power is typically used in industrial and commercial applications. Single-phase power is typically used in residential applications. When working with three-phase motors, it's important to ensure that the motor is properly connected to the three-phase power supply. Incorrect connections can cause the motor to run backwards or to overheat. Electrical diagrams and schematics are used to represent electrical circuits. These diagrams show the connections between electrical components such as motors, switches, and circuit breakers. Understanding electrical diagrams is essential for troubleshooting and maintaining electrical systems. Electrical testing equipment such as multimeters, clamp-on ammeters, and insulation testers are used to test electrical circuits and equipment. These instruments can measure voltage, current, resistance, and insulation resistance. Use electrical testing equipment to troubleshoot electrical problems and to verify the safety of electrical systems. When using electrical testing equipment, always follow the manufacturer's instructions and wear appropriate personal protective equipment. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other electrical disturbances. SPD divert the surge current to ground, protecting the equipment from damage. SPD are commonly used on electrical panels and non-sensitive electronic equipment. Power quality is a measure of the quality of the electrical power supply. Power quality problems include voltage sags, voltage swells, and harmonic distortion. Power quality problems can cause equipment to malfunction or fail. Power quality monitoring equipment can be used to identify and diagnose power quality problems. The results of the initial calculation, giving approximately 1119 watts, should be considered an estimation, and the motor's nameplate data should always be consulted for accurate values. Always prioritize electrical safety, follow applicable codes and standards, and seek assistance from qualified professionals when working with electrical equipment and systems.